Good morning, I'm Nigel Ward. I'll be talking about some software we've developed for corpus studies of phonetic reduction and other speech technology applications. This is a presentation for LREC, the Language Resources and Evaluation Conference 2026. Okay, so what is phonetic reduction? So in speech, people sometimes sound poorly articulated, or it's hard to understand them without the context, and that's reduction. Here's an example for you.
That one's so good. I love that one. That one's like a nice short one.
Okay, sounds pretty normal, but if you pay close attention, you'll notice that things like the T in that one is missing. It's that one's so good. I love that one. That one's like a nice short one. The word nice here, you can just hear a couple sounds. So that's phonetic reduction. So our tools take a speech signal, typically just a conversational utterance or two, and output an estimate of the perceived degree of reduction word by word. So, is it reduced or is it not reduced? The correlation with human judgments for English, it's okay, 0.38. And I should mention that humans don't agree about this too much either, so this is acceptable. For Spanish, it's a little bit lower, and the software, you can download it at the URL shown. So that's the talk. The rest is just details. One detail is that the generality of the tools are pretty good. So these are the correlations between human judgments again. It depends on the annotators, it depends on the dialog type, but generally it's around 0.4, 0.3 in that range. I mentioned human agreement a couple times. So here's a little table that shows, for example, that C and J, two annotators, correlated with 0.47 on a small sample of data. Others correlate a little bit lower. And it's kind of all over the map. People agree with each other or disagree with each other to different extents. The pairwise average for this little set of data was 0.47, and the model was 0.43. So not too shabby, not too far below what humans do. And for some annotator pairs, it's better than the humans. So for example, for D, trying to predict C annotations, the model does better than D did. So probably usable. Just to stress this one more time, previous tools have tried to produce predictions of reduction at the utterance level or the passage level if you're evaluating somebody for, say, some speech impediment or whether some surgery has improved that, but we can do it word by word, which is much more relevant for lots of pragmatic applications. All right, so the talk, what we built, I've already explained that. Next up is how we built it. So a couple approaches you could take if you're interested in modeling reduction in dialogue. You could look at correlates, and that's what most previous research has done. So phonetic reduction has different correlates. So you can look at the phonological rules, you can look at increased co-articulation. The most popular one in the literature has been to look at shorter durations. So in general, if you speak faster, if you speed up a word, if you say it like really short, like a function word, it will be reduced. So there's a strong correlation there, at least in some genres of speech, and people have exploited that. But really that's not a strong enough correlation. Reduction and shortening are two different things, and we really want to model reduction by itself. Intelligibility-based approaches are other things. You can have humans rate whether they could understand something or actually try and understand the word, and if they fail, you can conclude that, in fact, it was highly reduced. Or you can run an ASR system, a speech recognizer on it, and estimate the goodness of pronunciation. That also works, but intelligibility and reduction, again, they're two different things. So we came up with a purist approach. We're actually focusing on modeling human perceptions of reduction, what seems to people to be reduced. And here we use that definition that I showed you earlier in gray, subjective judgments of being poorly articulated or possibly hard to understand without context. Students in the lab very patiently annotated many minutes of dialogue for how reduced they were, where 0 is enunciated, 3 is highly reduced, and we have the other scales. And we always work with dialogue data. Here's a screenshot of the annotation tool we used, Elan.
It was a cool experience. Yeah, it was interesting. But I eventually got tired because I was doing the overnight shift.
And the students were mostly labeling interesting conversations, not just people speaking for the sake of speaking, but where they really got into it, because eventually the applications that we want to build will have really engaging AI partners. And there you see the annotations, 1s and 2s and 0s. Label distributions, they were fairly well distributed, and if you want to build your own models, you can download the data from the URL shown. Inter-annotator agreement, seldom did people actually agree perfectly on what the annotation level was. However, if you give them a little bit of margin of error, then the annotations are better. And in terms of kappa, the agreement was low. In terms of correlations, it looks a little bit more promising. In the paper, we have some thoughts on why people actually disagree on the annotations. All right, taking the annotations as given, though, we built our models. The first attempt failed, but we were inspired by the idea that reduction correlates well with some prosodic properties. So there's an idea in the literature that reduction is sort of the opposite of prominence. So if you stress a syllable or two, the opposite is unstressing or reducing things. And so those unstressed syllables tend to be lower in pitch, narrower in pitch range, and quieter. And this work is done based on laboratory studies where we have people come into the lab and read sentences like, "Did Joni make the marmalade?" "No, Marianne made the marmalade." And reliably, the second occurrence of marmalade will be reduced, and it will have those intonation correlates that I mentioned. However, in dialogue, the correlations with the various prosodic features are not so good, and sometimes they actually go the opposite way to what the literature suggests. So reduction in speech varies a lot based on the genre. And although true for English and Spanish, and although we attempted to build a model, the correlations were pretty low, so we abandoned that pretty darn fast. What we do, and what actually works, is use features from a pre-trained model. So speech LLMs or speech LMs or audio LMs, they have different names, are like large language models for speech. And we take the intermediate representations, here the 12th layer from the HuBert base, as features that we can then use to build a simple model. Since HuBert is pretty clever, it's got 12 layers of transformers and other magic inside, we use those features and trust them to contain almost all the information we need, and we just use a simpler linear regression model on top of that. We train it at the frame level every 20 milliseconds, we have it make a prediction where the targets are inherited from the word level labels, and then the word level estimates for reduction are based on the average of the per frame estimates. And here's what we get. So the bottom number there, the 0.376, that's the 0.38 that I mentioned is our headline reduction, our headline correlation. Just to stress, the frame level predictions are unstable. So here the black line is the average of human predictions. Human judgments actually vary a lot, but there's the green line for that. And the blue line shows approximately what the model is predicting at the word level. So the word level predictions are decently good. We often have a problem that they're shifted relative to the human judgments. We think this is because humans vary in the baseline degree of reduction that they use, and the model is not sensitive to this. But they do pretty well. However, if you look at the blue dots, the frame level predictions, they're all over the place. So don't use this model for frame level predictions. We explored different ways to get rid of noise. No real benefit was found. We found that Spanish is harder to predict. There's a couple of reasons for that discussed in the paper. And do not use an English-trained model to predict Spanish or probably any other language. So reduction is language dependent. All right, so that's what we built, how we built it, a little bit on why we built it. So our vision is of different styles of human-AI interaction. So if you think about human-robot interaction today, you might think of telling the robot, go to the kitchen, make me a sandwich. And 2 minutes later, it comes back and it's got a sandwich for you. That's fine, but as interactive becomes more intense, more collaborative, as you're actually doing things with robots in real time, you'll need a different style, more grunts, more prosody, more interaction. So to build those things out, we need more attention to prosody, not just the words that are said, but the tone, how they are said. And that's for the sake of conveying pragmatic functions like, yes, you're doing a good job lifting up that block. Oh, now we should stop right here and prepare to put the block in place. And of course, people don't really do that in conversation. They just say, good, okay, up, where it's all in the tone of voice. And when I say prosody here, I mean not just intonation. To elaborate, so I wrote a book a couple years ago where a major theme is that prosody is more than just the pitches ups and downs. It also involves things like harmonicity, lengthening loudness, creaky voice nasality, breathy voice, and reduction. At the time, we didn't have tools for estimating reduction in dialogue, so there wasn't much we could say. But we do know from the literature that reduction has a lot of meanings and functions. And our job for our lab over the next year or so is to extend that list, to figure out exactly, what are the pragmatic functions that reduction can serve. And just to clarify, this is not just a person reduces a word and that tells you something. It's the pattern of reduction together with high pitch and lengthening and maybe a little bit of creaky voice and some other things. It's those configurations that convey the meaning. If we have a corpus, we can do the analysis, discover those things, and now that we have tools for annotating reduction automatically, we can create that corpus. So far, we've done two little things. The first one was to examine the patterns of reduction before turn yields. So in conversation, sometimes people will just pause and then keep going. So the pause in that case was not a turn yield, but sometimes they'll actually have a little pause that ends the turn and invites the other person to comment or say something. So at the point before those turn yields, what does reduction do? Well, about a second before, there's a dip in reduction. Or in other words, people tend to pronounce the word about a second before turn yield a little bit more clearly. And then some reduction happens. So this is something that's being discussed in the literature, but here, by virtue of having the tool, we can apply this to 10,000 turn yields and find the pattern a lot faster. Our second little case study examined reduction before prominence. I mentioned prominence before. A prominent syllable is if I say something like, oh my goodness, look at the clock. Clock is prominent. Of course, we have high pitch, yada, yada, yada. But what's interesting is that before that, a few hundred milliseconds before that, there's a tendency to increased reduction. That makes sense if you want to mark something as prominent. Maybe you reduce the things in the vicinity to make it stand out more. But I don't think this has been discovered before, and we found it very easily just by statistical analysis. Incidentally, on the right, you see the pattern for a single speaker. The patterns are much clearer for some speakers. Other speakers don't have this pattern at all. Very speaker dependent. Other topics, so we have a journal article out last year which talks about how phonetic reduction is associated with positive assessment. That was the original example I gave you. That's a nice short one. If you're feeling positive about something sincerely, you tend to reduce. Note that speech synthesizers don't do this. Speech synthesizers always sound cold and robotic. Maybe this is why. And so now that we have a tool to automatically annotate large corpora for the degree of reduction, word by word, we have the potential to train up speech synthesizers that can vary systematically the degree of reduction and that you can control. And you can use that, we imagine, for better conveying various pragmatic functions. So far, the results are mixed. We have a first paper just submitted, but we need to continue to work on this topic. And we hope others do also. That's kind of it. Thanks to all the people and institutions who helped us. And you can shoot me a mail if you have comments or questions.